Hey, welcome back. In this video, we're going to talk about an excellent application of exponentials in a physics application, specifically Newton's law of cooling. In this case right here, what Newton's law of cooling states is that the temperature of an object at time t can be modeled by this exponential. And importantly here, this case is T sub s right here is the ambient or the air temperature. And what you'll notice is this formula is stating is that the temperature of an object will react in an exponential decay type model with this additional addition of the surrounding air temp. And that should make sense if you think about transformations of functions. This is saying, well, it doesn't go to zero if the surrounding temperature, let's say, is 80 degrees or 75 degrees will be in our first example, is the temperature of that object won't go below that. So it creates like this horizontal asymptote for the temperature of the object is given by the surrounding temperature, the ambient temperature. In this model right here, we should know the rest T is just time, whatever unit you'll be working with in minutes, hours, or seconds. A is the initial temperature. And that should feel very familiar with what we've seen before. The A in this model is always this initial amount. And we have this e to the kt, which we've seen in different contexts, but specifically right here, the K is considered the cooling rate. All right, then beautifully in these situations where we are given to ask about the temperature and something that's cooling, given some ambient temperature, we can just apply this right away. Again, we have this initial temperature and the surrounding temperature we will always should have. And in this case, we are given that. We're told that this steak comes off the grill and begins cooling at 145 degrees, and the air temperature around the steak is 75. So then according to Newton's law of cooling, we know that the temperature of the steak at time t, we'll talk about the units for t in 1 second, equals 145. So this is the initial temperature times e to the kt plus 75, which is the air or ambient temperature. And then as always with these exponential models, I just want to make sure I understand what I want t to be in this situation. The only time information we're given about is minutes. So I'm going to make sure that in this case, every time I use t, it's in terms of minutes. So Newton's law of cooling just says that the temperature change behaves in this way, that the object cools in this manner. Importantly, we don't have our entire exponential function or exponential model. Specifically, we don't have this k value. So the first thing we're going to do, or which is our cooling rate, we need to find this cooling rate or find k. In order to find K, we need a bit more information. We do know the initial temperature and the room temperature, but we need some more information to find that K value. And we have it right here in this statement that the steak is 135 degrees after 15 minutes. So what that statement right there means, importantly, given this model, is that T of 15, again, because I chose that my inputs would be in terms of minutes, so T of 15 equals 135. What I'm going to do now is use this information to find this K value. And what that means is that this function equals 135 when I input a 15 for T. So then given that information, I know that this function should output 135 when I input a 15 for T. So we'll write this e to the K now times 15 because T equals 15 plus 75. And so now what we're going to do, we only have one unknown. We're going to do the work of finding this K value right here. First thing I'm going to do is subtract 75 from both sides. So we get that 60 equals 145 e to the 15K right here. Then what I'm going to do is divide both sides by 145. That'll give me 60 over 145. But I want to reduce that if I can. So I'll write this first. 60 over 145 equals e to the 15K. I could just find the decimal approximation, but I've said this a few times, and this is really important when working with exponentials, is that rounding can get you really far off answers if you round early in a problem. So all I'm going to do is just avoid a decimal approximation as long as possible. I'll divide these, reduce this fraction, divide these both by 5 to get 12 over 29. equals e to the 15k. And now in order to solve for k here, I'm going to need to employ logarithms. I'm obviously want to use the natural log here because I have this base e. This works out really nicely. And importantly, I employed the natural log in this case because of what happens on the right-hand side of this equation, which gives us 15k, because this is the log base e of e to some power. So I just get out that exponent over there. On the left-hand side, I'm going to keep this as the natural log of 12/29. And then dividing by both sides by 15 will isolate k, so that I have k equals the natural log of 12/29 divided by 15. And then, unless I want to work with this pretty disgusting object right here, I do need a decimal approximation at this point. I've avoided it long enough. I put this into my calculator and found that this is negative 0.05883. And just to mention it again, I always suggest 5 decimal places when working with exponentials, though in your situation or the scenario, you might need more or less. But again, if you're rounding early in an exponential question, use at least 5 decimal places, or if you can, just save the values in your calculator and just use them over and over as much as possible, their fully expanded form, in order to be able to have a final answer accurate to a few decimal places. And now we found our full model for the cooling of this steak right here. We have our K value, so we can write this all out now. T of T, in terms of minutes again, is 145 e to the negative 0, or negative 0.05883 t plus 75. So there we have our full model for the temperature of the steak after t minutes, represented right here. But unfortunately, we haven't answered our question. Where being asked is when the temperature will be 120 degrees. But the beauty is, now that we have our model, all we have to do is set it equal to 120 and solve for t. So we want to know when the temperature of this steak will be 120. We know that temperature is modeled by this right here. And solving this is going to be very similar to when we were solving for k right there, because we're solving for an exponent. First thing I'm going to do is subtract both sides by 75. What I then get is 45 equals 145 e to the negative 0.05883 t. Divide both sides by 145. I'm going to use the same treatment I used before. This would be 45 or 145. I can reduce by a factor of 5, and so this 45 divided by 145 reduces down to 9/29, which equals e to the negative 0.05883 t. I'm now going to apply the natural log to both sides of this. Again, when I apply the natural log, that exponent will come down, and so what I get is 9/29 inside this natural log right here equals the natural log of this jazz. And then as solved, this side right here just becomes negative 0.05883 t, because this is log base e and this is an exponential base e. I'll keep this side the same again. And then what I'm going to do is divide both sides by this decimal right here. And so I'll do this all in one step. I'm going to plug into my calculator the natural log of 9 divided by 29, end parentheses, divided by negative 0.05883. And what I get is that this occurs in about 19.9 minutes. Or maybe if somebody wasn't being picky, you could just say right around 20 minutes. And as always in applications, I like to look back and say, does my answer make some sense? So given this situation, it started at 145 degrees. It's in temperature of 75. After 15 minutes, it had dropped to 135 degrees. And then about 5 minutes later, we're saying it's now down to 120. It seems reasonable given the situation. And again, just to backtrack all the way back, we had this base formula based on Newton's law of cooling, where we have an initial temperature once it stopped heating, or once we began cooling, however you want to think about it. 145 is the initial temperature at the start of cooling. T, by the way, represents the time since it started cooling. So this isn't 19 minutes or 20 minutes after this time right here. It's 20 minutes after when we pulled it off the grill, just to make that clear. We have this e to the kt part where k is going to represent this cooling rate and our ambient temperature. Always, if we're given this type of information, which is very common, our work first will be to find this k value. In order to find the k value, well, we either are given our cooling rate or we're given a situation that occurs after the initial temperature. In this case, we had that T of 15 equals 135. We plugged that in, solved for k, which gave us our final model. And then whatever question they throw at us, I mean, ask me anything about the temperature, like what temperature will it be? Or what will the temperature be after an hour? I can do that all now because I have the full model. In this case, to solve for when it's going to be 120 minutes, I just set the temperature equal to 120 and solve the exponential equation. If again, vice versa, they said something like, what's the temperature after 20 minutes? I would just plug in a 20 for T and solve that. It sure as heck should come out something close to 120 because this is about 20 minutes.